Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to take a second and just visualize the most likely place we might finally find alien life in our solar system.
Yeah, that's a big question.
Right. And, if you ask 100 people on the street, the vast majority are going to point straight to Mars.
Oh, absolutely. The red planet.
Exactly. Mars. I mean, it's right next door. We have all these rovers, leaving tire tracks and the dirt everywhere.
We spend so much time looking at those dried up riverbeds.
Yeah, just hoping to find, a fossilized microbe from billions of years ago. But I want you to completely bypass Mars today.
Just skip it entirely?
Totally. Forget the red dust. Forget looking for ghosts of a dead biosphere. We are heading much further out into deep space, past the asteroid belt.
Straight toward Jupiter.
Straight to the gas giant. But, we aren't looking at the turbulent atmosphere of Jupiter itself. We are locking our sights on one of its icy moons.
Europa.
And our mission today is to explore this massive, brand new reality check in astrobiology.
It's a huge shift in how we think.
It really is. Because, we've known for a while that Europa hides this global ocean beneath its frozen shell.
Right. That's not the new part.
No, but the new part is that getting to that water and, whatever complex chemistry might be swimming around in it is going to be a much tougher barrier than scientists ever assumed.
It is arguably the most compelling piece of real estate in our entire planetary neighborhood.
Why is that exactly?
Primarily because it's not a fossil. It is active right now. When you look at high-resolution images of Europa...
Ones from the Galileo probe, right?
Yeah, the Galileo probe in the 90s, or even the more recent stuff from Juno, you immediately notice what is missing.
Craters.
Exactly. You don't see craters. If you look at our own moon, it is absolutely pulverized, just covered in impact craters from, billions of years of cosmic bombardment.
It's a giant golf ball.
Right. But Europa doesn't have that. You see this brilliant, bright, white sphere, heavily scarred with these incredibly long, dark, sort of reddish-brown fractures.
It literally looks like a cracked eggshell floating in the void.
That's a perfect way to describe it. And the lack of craters tells us something vital. The surface is young. It is constantly refreshing and renewing itself.
Because beneath that cracked shell, Europa is hiding a massive global ocean of liquid water.
And not just a subterranean lake either.
Right, not a slushy aquifer. It is a deep, churning ocean that wraps around the entire moon.
Which brings us to why astrobiologists are just so obsessed with this place. It comes down to what we consider the holy trinity for habitable environments.
The 3 non-negotiable ingredients for life.
Exactly. If you are looking for life as we know it, first, you need liquid water.
Not ice, right?
No, ice is rigid, it traps molecules, and not vapor because that's too diffuse. You need a liquid medium where molecules can float, interact, bond.
It's the universal solvent.
Right. Second, you need the right chemistry. You need the building blocks.
Like carbon, hydrogen, nitrogen.
Oxygen, phosphorus, and sulfur. The CHNOPS elements.
CHNOPS. I always like that acronym.
Yeah.
And the assumption is that those elements are present on the rocky seafloor of Europa, right?
That's the running theory, yes.
So the water is in direct contact with a silicate mantle, meaning the ocean is likely dissolving minerals and salts, creating this rich chemical soup.
That direct contact is so crucial. It's what differentiates Europa from a moon like, say, Ganymede.
Because Ganymede has an ocean, too.
It does, but Ganymede's ocean is likely sandwiched between 2 layers of impenetrable ice.
Oh, so it never touches the rock.
Exactly. Europa's ocean is interacting with the rock. But that brings us to the third crucial ingredient for life.
Energy.
An energy source. You need something to drive the chemical reactions to take those basic elements and force them to assemble into complex organic molecules.
And on Earth, the vast majority of our biosphere relies on the sun.
Photosynthesis, right.
Plants use the sun, and then everything else basically eats the plants.
Yeah.
But out in the Jupiter system, the sun is just like a bright star in the sky.
It's incredibly faint out there.
The solar radiation is just a fraction of what we get here on Earth. So the sun isn't providing the energy for life.
And it certainly isn't providing the heat to keep a global ocean from freezing solid.
Because space is unimaginably cold. So how does a moon floating hundreds of millions of miles away from the sun, out in the freezing depths of the outer solar system, actually manage to stay liquid?
Well, if Europa were just floating out there in isolation, it would be a solid, inert block of ice all the way through to its core.
Just a giant ice cube.
Literally. The surface temperature at Europa's equator never gets warmer than about minus 260 degrees Fahrenheit.
Wow.
And at the poles, it drops down to an agonizing minus 370 degrees.
That is just, I can't even comprehend that level of cold.
Any ambient heat from its formation billions of years ago should have radiated away into the vacuum of space a long time ago.
So the heat keeping that ocean liquid has to be continually generated from the inside out.
Exactly. It's the engine keeping Europa alive.
And that engine is driven entirely by gravity. Like, we have to picture the sheer, overwhelming gravitational pull of Jupiter.
Jupiter is a monster. It's 318 times more massive than Earth.
Right, so Jupiter's gravity, it completely dictates the physical reality of its moons.
And Europa is caught in this very specific gravitational dance. It is in what we call an orbital resonance with two of Jupiter's other large moons, Io and Ganymede.
Orbital resonance, so they are synced up.
Yes. For every one time Ganymede orbits Jupiter, Europa orbits twice, and Io orbits 4 times.
Okay, the 4-2-1 resonance.
Right. This Laplace resonance forces Europa's orbit to be elliptical or oval-shaped rather than a perfect circle.
So the distance between Europa and Jupiter is constantly changing.
Exactly. Sometimes Europa swings in relatively close to the gas giant, and other times it swings much further out.
And that changing distance means a constantly changing gravitational pull.
Yes. When Europa makes its closest approach to Jupiter, known as the perigove, Jupiter's gravity pulls on the moon with immense force.
It literally stretches the moon, doesn't it?
It does. The solid rock of the mantle and the thick ice shell actually bulge outward toward Jupiter by as much as 30 meters.
That's like 100 feet. Solid rock and ice bulging up 100 feet.
Right. And then, as Europa swings further away in its orbit, reaching apogee, that gravitational grip relaxes.
And the moon's shape settles back down.
Exactly.
So an entire planetary body is being physically stretched and compressed 100 feet up and 100 feet down every single orbit.
Which takes about 3.5 Earth days.
That is insane. Just think about the mechanical stress of that. I mean, it's like, okay, if you take a thick metal paper clip
Okay.
and you just hold it, nothing happens.
Yeah.
But if you start bending it back and forth rapidly and repeatedly,
The metal right at the bend gets hot.
right, you can actually burn your fingers on it. The friction of the metallic crystalline structure grinding against itself generates internal heat.
That translates perfectly to a planetary scale.
So Jupiter is basically bending Europa like a paperclip.
The continuous squeezing and stretching is bending that planetary paperclip. The massive amounts of rock deep in the moon's silicate mantle are grinding against each other.
And the layers of deep ice are flexing too.
Yes. All of that incredible internal friction generates an enormous amount of thermal energy deep within the moon's interior.
Tidal heating.
Exactly. Tidal heating. It is a ceaseless, powerful geologic engine.
So this immense heat is radiating outward from the rocky core. It hits the bottom of the frozen crust, melting it from the inside out.
Creating this massive, warm, global ocean hidden in the dark.
Right. The ocean exists in this state of tension. It's sandwiched between the hot, volcanically active, rocky seafloor below and the frozen ice shell above.
Yes.
But wait, I have to push back here. If there is so much heat being generated inside this moon enough to melt a volume of water twice the size of all of Earth's oceans combined, why doesn't the heat just melt the rest of the ice?
That's a great question.
Why is the outside still frozen solid? It seems like it should just be a water world.
Because you are witnessing a stalemate between two extreme thermodynamic forces.
Okay, a stalemate.
You have the intense, constant tidal heating pushing up from the seafloor, but you also have the brutal, unforgiving cold of deep space pressing down from above.
All right, the minus 260 degrees.
Thermodynamics dictates that heat will always move to where it is cold. The thermal energy from the ocean is constantly trying to bleed away into the vacuum of space,
And as a result, the outermost layer of the water freezes.
creating the thick ice shell.
And once that ice forms, it changes the dynamic, right? Because ice is a remarkably good insulator.
It acts as planetary armor. The ice shell traps the remaining heat inside, preventing the rest of the ocean from freezing solid.
Wow.
It is a delicate equilibrium. The ice shell is estimated to be anywhere from 10 to 15 miles thick.
15 miles.
Perhaps even thicker in certain regions depending on the localized heat flow from the mantle.
So we have this incredible, potentially life-bearing ocean, complete with the chemistry and the energy needed to sustain a biosphere.
Yes.
But it is locked inside a planetary vault with walls made of miles-thick, rock-hard ice.
Which creates an absolute nightmare for planetary scientists and engineers.
I can imagine. How do you sample an ocean you can't reach? We don't have the technology to pack a 15-mile-long drill onto a rocket.
Right. No, we definitely don't.
And then fly it to Jupiter, land it softly on the ice, and power it for years as it grinds through cryogenic ice. That's just science fiction.
Completely. Which is exactly why the scientific community has spent the last few decades clinging to the dream of the shortcut.
The shortcut? Okay, let's unpack this. What was the assumption here?
The shortcut was a highly optimistic yet theoretically grounded assumption about the mechanics of the ice shell.
Hoping we wouldn't need a gargantuan drilling operation.
Right. The hope was that the ocean was actively doing the hard work for us, that the ocean might be migrating up to meet us.
Because we're looking at a surface covered in thousands of miles of chaotic fractures, ridges, and bands.
The shell is clearly active.
So the theory was that deep ocean water could travel upward through narrow vertical fractures in the ice.
Geological features known as dikes.
Yes, and that this pressurized water would pool in shallow reservoirs much closer to the surface, like maybe just a few dozen meters down.
That was the dream. The scientific framework for this is cryovolcanism.
Ice volcanism.
Exactly. To conceptualize it, scientists naturally looked at the geologic processes we understand best.
Traditional volcanism here on Earth.
Right. Beneath our feet, we have incredibly hot, pressurized, molten rock magma moving through the lithosphere.
And when this magma encounters weak points, faults, or tectonic fractures in the Earth's crust,
the immense lithostatic pressure forces it upward. Sometimes it erupts explosively on the surface as lava.
Or it pools in shallow magma chambers just below the crust, creating geothermal anomalies.
Exactly. Cryovolcanism takes that entire Earth-based plumbing system and applies it to an ice world.
So instead of molten silicate rock moving through a rocky granite crust, you have liquid water moving through cracks in a solid water ice crust.
Yes. The deep ocean is highly pressurized by the weight of the ice above it.
The ice shell flexes, a crack opens up at the bottom, and that pressure squeezes the liquid water up into the fracture.
That was the prevailing model for a long time. If cryovolcanism operates on Europa with the same fundamental mechanics as volcanism on Earth, you would expect these vertical dikes to act as natural pipelines.
Continuously ferrying deep, mineral-rich ocean water up into shallow pockets just beneath the surface.
Or even erupting onto the surface to create the smooth, renewed plains we see in the orbital imagery.
I mean, this would be the ultimate game changer for exploration. If this shortcut exists, future space missions wouldn't need a 15-mile drill.
They could simply use ground-penetrating radar from orbit to map out these shallow pockets.
Right. Then you land a relatively small, simple probe equipped with like a thermal melt probe.
You melt through maybe 10, 20, or 50 feet of ice.
And suddenly you are sampling the deep ocean. You are tasting the exact chemical environment where life might be thriving without having to breach the primary 15-mile vault.
It was an incredibly elegant solution to an impossible engineering problem.
What?
But as we often find in planetary science, mapping the mechanics of one planet directly onto another is fraught with peril.
I mean, wait, ice and liquid water are fundamentally different materials from solid rock and molten lava.
Completely different.
Can we really assume they behave the same way under pressure?
No, we can't. They possess completely different thermodynamic properties, different densities, and they transfer heat in entirely different ways.
And this is where the dream of the shortcut collides with a massive, sobering reality check.
A major 2026 study has completely dismantled this assumption.
Yeah, led by Lujendra Oshah, a planetary scientist at the Rutgers School of Arts and Sciences.
They finally ran the brutal, unfiltered physics on this concept.
Because they didn't want to rely on Earth-based analogies anymore. They wanted to know exactly what happens when liquid water tries to force its way through deep space ice.
And their methodology was focused entirely on the journey itself. The core question they tackled was whether liquid water could realistically rise from Europa's deep, highly pressurized ocean, travel vertically through narrow fractures in the ice shell, and reach the shallow subsurface without freezing solid along the way.
And to answer a question like that, you can't just rely on telescope observations. You have to build the environment in a computer.
They utilized advanced computational fluid dynamics to simulate the localized physics of this upward journey.
Modeling the pressure, the temperature gradient of the ice shell, the specific heat capacity of the water.
And the geometry of the fractures.
And in doing so, they exposed a critical flaw in the older models, the models that had generated so much optimism.
Yes. The previous models relied heavily on a mathematical simplification. They treated the rising water as if it moved in a laminar flow.
Laminar flow. Okay, let's make sure we have a vivid picture of this, because it is the linchpin of the old theory.
It is.
Laminar flow is smooth. It's highly orderly. Like if you turn on your kitchen faucet just a tiny bit, and the water glides out in this perfect, clear, glass-like cylinder where all the water molecules are moving perfectly parallel to one another.
With no cross currents or mixing?
Right. That is laminar flow.
The old models effectively assumed that water from the deep ocean would behave like that faucet. It would gently and smoothly slide up these fractures in the ice.
Which sounds nice in theory.
In a laminar flow regime, the water maintains its thermal energy relatively well because the fluid isn't mixing.
So only the very outer layer of the water touches the freezing ice walls.
Exactly. It acts as an insulating buffer for the warmer water in the center of the flow.
But Ojha's team realized there was a fundamental physics element missing from those assumptions.
Applying laminar flow to a highly pressurized extrusion event on an active moon was a mathematically convenient but physically impossible assumption.
Because space isn't a controlled laboratory. You can't expect millions of gallons of pressurized water to flow up a jagged, dynamic, freezing pipe in a smooth, straight line.
The older models were completely ignoring the chaotic, unpredictable nature of fluid dynamics.
They were ignoring turbulence.
Turbulence dictates the reality of the flow. When you factor in the intense pressures at the bottom of the ocean, the narrow, jagged constraints of these tectonic fractures, and the immense vertical distance the water must traverse,
A gentle laminar stream is physically impossible.
the fluid dynamics simulations proved that the water wouldn't rise peacefully. It would be injected into the fracture at high velocity, resulting in violently turbulent flow.
And if the water is turbulent, the molecules aren't moving in a straight parallel line anymore. The fluid is tearing itself apart.
It is moving left and right, surging up and dropping down.
It is swirling aggressively, creating massive eddies and vortices inside the crack.
Picture a raging whitewater river violently rushing through a narrow, jagged slot canyon.
Oh, wow. Yeah.
The water is crashing against the rock walls, folding over on itself, constantly churning and mixing.
Now take that chaotic energy and place it inside a vertical crack in Europa's ice shell.
You have a churning, swirling mass of liquid water violently scraping and mixing against the walls of the fracture.
And we have to focus on the thermal reality of those walls. This isn't a rocky canyon in Arizona.
No, and it isn't the relatively warm ice you'd find in an Earth glacier either.
This is deep space ice.
Yeah.
As you move up through the shell, the temperature of the ice drops precipitously, plunging down toward that surface temperature of minus 260 degrees Fahrenheit.
It is a cryogenic environment.
Which triggers the fatal mechanism that destroys the shortcut, right? Catastrophic heat loss.
Yes. In our earlier laminar flow example, the water in the center was insulated. But in a turbulent flow, there is no center.
Because it's constantly mixing.
The swirling motion constantly takes the relatively warm water from the interior of the crack and violently throws it outward, smashing it directly against the freezing cryogenic walls.
So the water rapidly surrenders its thermal energy into the surrounding ice.
The rate of heat transfer is staggering, far faster than any of the older, simplified models had accounted for.
The water is rushing up, furiously churning, and rapidly hemorrhaging its heat into the walls of the fracture. It cools down at a phenomenal rate as it climbs toward the surface.
And this rapid cooling in a chaotic environment leads to a state of matter that dictates the final outcome.
Supercooling.
Supercooling. It is a fascinating thermodynamic state.
Because we generally assume that the instant water reaches 32 degrees Fahrenheit or 0 degrees Celsius, it immediately transitions into a solid state.
Right, but the phase change from liquid to solid requires a starting point, a nucleation site, for the ice crystals to begin forming.
And if it doesn't have one.
If the water cools down rapidly enough, it can actually drop below its standard freezing temperature and temporarily remain in a liquid state.
This is supercooled liquid.
Yeah.
We see this on Earth under very specific conditions, right?
We do.
Like if you leave a perfectly sealed bottle of highly purified water in the freezer just a little too long, you can pull it out and it still looks completely liquid. It might be like 25 degrees Fahrenheit, but it's flowing. However, the moment you flick the bottle with your finger or twist the cap and release the pressure,
You introduce a mechanical disturbance.
you provide a nucleation point, and the entire bottle flashes into solid ice right in front of your eyes in a matter of seconds.
The water in that bottle is thermodynamically unstable. It desperately wants to freeze. It just needs a trigger.
Now apply that to Europa. The turbulent water rushing up the fracture becomes deeply supercooled by the constant contact with the cryogenic walls.
And in that violently churning, highly pressurized environment, there is no shortage of mechanical disturbances or nucleation sites.
The ice walls themselves provide infinite points for crystallization to begin.
So the supercooled water starts to flash freeze.
But because it's moving so violently, it doesn't freeze into a single smooth sheet of solid ice from the outside in.
It forms something entirely different. It forms Brazil ice.
Brazil ice, that's a specific term.
Yes, Brazil ice is the nail in the coffin for the cryovolcanism theory on Europa.
What exactly is it?
When this highly agitated, supercooled fluid begins to freeze, it instantly forms billions of tiny, needle-like microscopic ice crystals suspended directly within the liquid column.
So it stops being a fluid and turns into a thick, gritty, abrasive slush.
Exactly the consistency of slush. And as the turbulent flow continues to bleed heat into the walls, more and more of these Brazil ice crystals precipitate out of the liquid.
So the concentration of ice crystals skyrockets.
They begin to clump and stick together, increasing the viscosity of the fluid. More importantly, they aggressively stick to the incredibly cold, jagged walls of the fracture.
They start to accumulate. They are actively paving the inside of the crack with sticky slush, narrowing the pathway by the second.
It's like trying to pump rapidly setting concrete through a pipe.
The more it flows, the thicker it gets until it chokes itself out.
The timeline generated by OSHA's computer simulations is the most sobering aspect of the study.
Because of how fast this happens.
Given the rapid, turbulence-driven heat loss and the explosive formation of Brazil ice, these vertical dikes simply cannot sustain flow.
The models demonstrated that these narrow cracks wouldn't stay open for years or months or even weeks.
They would violently freeze shut within a matter of mere hours.
Hours. A massive tectonic fracture rips open at the bottom of the ice shell. The pressurized liquid ocean rushes in, hoping to find a path to the surface.
It immediately becomes turbulent.
It supercools, the Brazil ice forms a dense slush, and within a few hours, the entire fracture cements itself shut.
The fluid never even gets close to the surface.
Nature essentially slams the vault door shut the moment the ocean tries to escape.
The physics of the environment make the process brutally self-defeating. The very act of the pressurized water forcing its way upward generates the fluid turbulence that rapidly seals its own exit pathway.
The mechanics of the ice shell actively prevent cryovolcanism from functioning the way volcanism functions on Earth.
Exactly.
Okay, but I have a question. Looking at the scale of Europa, a moon subjected to the immense gravitational torture of Jupiter, couldn't we just assume the cracks are bigger?
You mean wider fractures?
Yeah. If a narrow pipe freezes shut in hours, what if the fracture is a massive, gaping chasm in the ice? Surely a massive fracture could survive the cold.
It's the logical next step in the hypothesis.
Right. If the pathway is wide enough, wouldn't sheer volume allow at least some of the water in the center to survive the journey and pool near the surface before the edges manage to freeze?
OSHA's team rigorously tested that exact scenario. They adjusted the simulations to account for significantly wider fractures, pushing the boundaries of what is geologically plausible for the ice shell.
Right.
The results were incredibly stubborn. Even under the most idealized, generous conditions, maximizing the width of the fractures, the upward migration still fails.
Wait, really? Why does scaling up the width fail to solve the thermal problem?
Because fluid turbulence does not scale linearly in a way that protects the heat.
Okay, unpack that for me.
Yes, a much wider fracture possesses a greater volume of water, and technically it takes slightly longer to freeze completely shut compared to a narrow crack.
That makes sense.
But the chaotic energy of the turbulence scales up alongside the volume. The violent mixing continues to throw the interior heat against the cryogenic walls.
So it's just mixing even more aggressively.
To successfully transport enough liquid water to the upper crust to carve out the vast geological features we observe on the surface, the massive lenticulae, the sprawling chaotic terrain, the fractures would need to be unrealistically massive.
They would require a width or a frequency that simply defies the structural integrity and the physical limits of Europa's ice shell.
Exactly.
It's like a battle of thermal mass versus environmental hostility. Like if you take a standard garden hose, fill it with warm water, and snake it through a frozen snowbank while violently shaking it, the water freezes almost instantly.
Right.
If you upgrade to a massive high-volume fire hose and do the same thing, the sheer volume means more water gets through initially. But if the walls of that fire hose are minus 200 degrees and the water inside is churning violently, that fire hose is still going to freeze solid before the water can establish a sustained long-term flow.
The cryogenic environment is just too overwhelming. The thermodynamic reality is absolute.
So no matter how much water you pump, the cold walls and the chaotic flow are going to freeze it solid before it reaches the other end.
The ice shell is too thick, the ambient temperature is too low, and the fluid dynamics are too chaotic for any localized volume of deep ocean water to punch its way through to the surface without surrendering all of its heat and freezing solid in the attempt.
This realization forces us into a very uncomfortable corner regarding our maps of Europa.
It does.
Because planetary geologists have spent decades analyzing the images from the Galileo mission. We see vast regions of chaotic terrain where the ice looks like it has been shattered, melted, and refrozen into massive, jagged blocks.
We see these features that unequivocally look like they were formed by liquid water interacting with the shallow crust.
In fact, based on radar and gravitational data, many scientists are heavily invested in the idea that there are distinct, shallow lenses of liquid water trapped in the ice just below the surface right now.
Yes.
But if OSHA's physics are correct, and the deep ocean absolutely cannot make the vertical journey, where did that shallow water come from?
This leads to the most critical and perhaps most disappointing astrobiological consequence of the study, the concept of the false hope.
The false hope of shallow reservoirs.
If we identify pockets of liquid water residing in the shallow subsurface of Europa, the physics dictate that they almost certainly did not originate from the deep global ocean.
If they didn't migrate up from the bottom, the only logical conclusion is that they were generated right there inside the upper layers of the crust.
Precisely the conclusion we are forced to draw. The alternative origin mechanism is localized heating and melting occurring entirely within the confined matrix of the ice shell itself.
But how do you generate enough thermal energy to melt massive pockets of liquid water entirely within a cryogenic ice shell, completely isolated from the hot, rocky core?
We return to the primary engine tidal heating.
From Jupiter.
The gravitational squeezing and stretching from Jupiter doesn't just affect the rocky mantle. It flexes the entire 15-mile-thick ice shell.
As the moon orbits, the ice is subjected to immense tectonic stress. It bends, it shears, and it grinds against itself along massive fault lines.
And in certain concentrated areas, perhaps where the ice is structurally deformed, the mechanical friction of the ice aggressively grinding against itself, shear heating, can generate enough localized thermal energy to literally melt the surrounding ice in situ.
So the mechanical friction melts the ice right where it sits. It's the planetary equivalent of vigorously rubbing your hands together when you're out in the cold.
That's exactly what it is.
The friction generates a small pocket of heat right between your palms, entirely independent of your body's core temperature.
Right.
So Europa's crust is constantly rubbing together, generating enough friction to melt localized pockets of slush and liquid water miles above the actual ocean.
It creates a shallow, isolated reservoir of liquid. And to a remote sensing instrument, like a radar sander looking down from a spacecraft in orbit, a pocket of liquid water simply registers as a pocket of liquid water.
But the distinction between those two origins is an absolute heartbreak for anyone designing a mission to find life. It completely changes the value of the target.
It alters the astrobiological potential of that water from a prime target to a virtually sterile puddle.
Because if we go back to the holy trinity of life, water, chemistry, and energy, we know life needs the complex, nutrient-rich chemistry that is only happening down in the deep ocean, where the water is actively dissolving minerals from the rocky seafloor.
That is where the hydrothermal vents would be. That is where the organic building blocks are churning.
If a space probe samples a shallow puddle that just melted locally, it's completely disconnected from the deep ocean environment. If a future multi-billion-dollar space probe lands on Europa, manages to melt its way through 50 feet of ice, and successfully samples one of these shallow reservoirs, and it turns out that reservoir was just created by mechanical friction, melting a block of pure, sterile ice.
It is completely disconnected from the biosphere. The scientific return would be profoundly limited.
It won't tell us what's happening in Europa's most intriguing, potentially life-bearing zone.
It would be akin to a marine biologist attempting to study the bizarre, complex hydrothermal vent ecosystems of the Mariana Trench by analyzing a puddle of melted snow sitting on top of a glacier in Greenland.
Wow. Yeah, physically they are both liquid water.
Yes, but one is a rich, dynamic chemical ecosystem and the other is just melted precipitation.
A shallow reservoir on Europa, if formed entirely by localized shear heating within the crust, will tell us absolutely nothing about the chemical conditions, the potential habitability, or the presence of life in the deep ocean.
It's a brutal bait and switch. We spent decades hoping these shallow pockets were a convenient window into the deep ocean.
But this research suggests they are just a mirror, reflecting only the isolated, frozen, sterile reality of the crust itself.
While it is undeniably a sobering realization for our immediate exploration goals, it is also a vital, timely piece of scientific course correction.
Because this discovery isn't just theoretical, is it?
No, this theoretical modeling isn't just an academic exercise confined to a university server. This new understanding of fluid dynamics and fossil ice has immediate, massive implications for billions of dollars of space hardware currently flying through the void of the solar system.
We're looking at the incoming fleet. The stakes here are incredibly high because we have 2 flagship missions already launched, already on their way to the Jupiter system.
And they were designed, funded, and built based largely on the older, more optimistic assumptions about Europa's ice shell.
Let's break down the timeline. First, we have the European Space Agency.
The European Space Agency launched the Jupiter Icy Moons Explorer, universally known as JUICE, in April of 2023.
Okay, so that's already out there.
It is currently executing a complex, looping trajectory through the inner solar system to build up speed, and it is scheduled to finally arrive in the Jupiter system in July of 2031.
And right on its heels, we have NASA's massive contribution to the effort, the Europa Clipper.
Right.
It launched recently in October of 2024. It is taking a more direct gravitational trajectory and is slated to arrive at Jupiter ahead of JUICE in April of 2030.
These are monumental engineering achievements. The Europa Clipper, for example, is the largest spacecraft NASA has ever developed for a planetary mission.
It's huge.
It will enter a highly elliptical orbit around Jupiter, designed to sweep past Europa and make 49 incredibly close, low-altitude flybys.
And it carries a massive payload of 9 highly sophisticated scientific instruments designed to map the moon's surface, composition, and interior structure in unprecedented detail.
And one of the most critical instruments on that payload, the REASON instrument, which stands for Radar for Europa Assessment and Sounding. Ocean to near surface is directly impacted by OCHA's research.
This is a powerful, ice-penetrating radar. Its primary directive is to fire radio waves down into the ice shell, measure how those waves bounce back, and map out the internal structure.
It is specifically hunting for the dielectric signature of liquid water. It is looking for those shallow reservoirs.
Without the sobering reality check provided by the fluid dynamics modeling, consider the scenario when Clipper arrives and powers up that radar.
The potential for a massive false positive is glaring.
Right. Clipper conducts its low-altitude flybys, the radar pings the upper layers of the ice shell, and the data lights up.
The radar waves hit a boundary transition from solid ice to liquid water and bounce back.
The science teams back at the Jet Propulsion Laboratory look at the telemetry. They see a massive pocket of liquid water just a few miles down, and they celebrate. They announce to the world that they have found it.
They'd think the deep ocean is venting upward, just like the old cryovolcanism models predicted.
But they would be wrong.
They would look at a localized, shear-melted pocket of sterile water and fundamentally misinterpret it as a direct, active chemical window into the deep global ocean.
And the danger of that misinterpretation extends far beyond a single press conference.
It dictates the future of space exploration for decades. They might use that flawed interpretation to lobby for, fund, and design a subsequent astronomically expensive lander mission targeted directly at that specific reservoir.
Fully believing they're about to drill down and sample the habitable zone.
A lander mission that would take another 20 years to build and fly.
They would finally land on the ice, deploy a thermal drill, melt their way down to the water, activate their mass spectrometers to look for complex organic molecules,
And find absolutely nothing.
sterile, isolated, friction-melted water.
It would be a catastrophic, generational waste of time, engineering, and scientific funding.
This highlights why theoretical modeling, Simulation and constantly challenging our own assumptions are the bedrock of planetary science. OCHA's research acts as a preemptive, critical guidebook for the scientists who will be analyzing the data from Clipper and JUICE.
It shatters the easy dream, but it sharpens the actual science. It forces the teams to be far more rigorous in their analysis.
When Clipper and JE arrive in the early 2030s and start beaming back petabytes of radar and gravitational data, the mission scientists now possess a crucial piece of the puzzle.
They know that the ice shell is a much more formidable, actively defensive barrier than they ever assumed.
So the data won't trick them into a false sense of victory.
They will know to treat any evidence of shallow liquid water with extreme skepticism regarding its origin.
It completely redefines the parameters of the search. If they find a shallow pocket, they can't just assume it's ocean water.
They have to analyze the surrounding geologic context. Is there evidence of massive shear faulting nearby that could explain it as localized melt?
They will know they either have to calibrate their instruments to look much, much deeper, trying to penetrate the full 15 miles.
Or they have to look for incredibly rare, catastrophic geological anomalies, perhaps massive impact basins where a comet punched a temporary hole through the Brazil ice barrier.
It forces the scientific community to be much smarter and much more discerning about the data they are about to collect.
Science is just as much about closing doors as it is about opening them. Proving that a specific pathway is physically impossible is a highly valuable scientific return.
It prevents the entire field of astrobiology from wandering down a theoretical blind alley for the next 20 years.
Exactly.
So synthesizing this entire reality check, we began with a vision of Europa that was deeply appealing. We pictured an accessible oasis, a dynamic, cracked, icy shell that was constantly bleeding its deep, warm, potentially life-filled ocean out toward the surface,
offering up its secrets for us to easily scoop up.
We banked entirely on the dream of the shortcut.
We relied heavily on terrestrial analogies, assuming that the mechanics of magma and rock would neatly translate to water and cryogenic ice.
We envisioned a complex plumbing system of dikes and fractures driven by the pressure of the ocean.
But then the brutal, unforgiving reality of computational fluid dynamics was applied.
The researchers at Rutgers pulled back the curtain on the actual mechanics of an alien moon. We were forced to abandon the calm, orderly, mathematically convenient assumption of laminar flow and plunge into the chaotic, violent, and thermally destructive reality of high-velocity turbulence.
We saw how that fluid turbulence aggressively strips the thermal energy away from the water, violently transferring the heat into the cryogenic walls of the tectonic fractures.
We witnessed the rapid onset of supercooling.
And we saw the fatal mechanism, the supercooled water flashing into billions of needles of Brazil ice,
instantly creating a highly viscous, gritty slush that aggressively adheres to the walls, cementing the massive fractures shut within a matter of hours.
It is nature's own impenetrable fail-safe mechanism. The very act of the pressurized ocean trying to violently force its way to the surface generates the exact chaotic conditions that seal its own fate.
The vault actively locks itself. And because of that physical reality, the shallow reservoirs we are hunting for with the upcoming radar instruments on Clipper and JUICE are likely just phantoms.
They are localized melt pockets generated by tectonic friction, entirely disconnected from the rich, complex, habitable zone of the deep ocean.
The barrier remains intact and the ocean remains profoundly isolated.
Which leaves us with a lingering, immensely daunting thought for the future of astrobiology and human engineering.
What's that?
We now understand precisely how formidable Europa's ice shell truly is. It is not a passive layer of frozen water. It is an active, self-sealing, dynamic armor that brutally shuts down even nature's own immense gravitational and thermodynamic forces attempting to push water to the surface.
If an entire pressurized ocean, driven by the relentless, grinding tidal forces of the largest planet in our solar system, cannot physically punch a hole through that cryogenic armor.
If nature cannot break the vault, what kind of radical, out-of-the-box, entirely unprecedented engineering will humanity eventually need to invent to pierce that armor ourselves?
That is a staggering thought.
Yeah.
If we are truly committed to touching that dark ocean below, we can no longer rely on the hope of a natural shortcut.
We cannot wait for the ocean to come to us. We are going to have to figure out how to break the planetary vault ourselves.
It forces us to ask just how badly we want to know what is swimming in the dark down there. When we started, we wanted to find an easy path to alien life. We thought Europa was going to cooperate.
We thought we could just skim the surface and find the answers.
But Europa is fiercely protective of its environment. The diagnostic landscape here isn't just murky. It is actively sealed under 15 miles of the hardest, coldest, most defensive ice in the solar system. The shortcut is closed.
The real grueling work of exploration is just beginning.
Keep looking up and keep questioning what you think you know.